Good evening, everyone. Welcome to the 12th and the final problem-solving session of the course Computational Continuum Mechanics. So, as you know, I'm Naresh. I'm a research scholar at the Department of Civil Engineering at the Indian Institute of Science. And the topic for today is solution procedures. So, if we recall what we have been doing so far, so here is a quick review of what we have been doing in this course so far. So we started off with So we started off with the idea of nonlinearity, the idea of nonlinearities in mechanics, the various kinds. We looked at material, geometric, and boundary nonlinearities. Then we looked at the kinematics, which is even before kinematics, we looked at some mathematical preliminaries we saw some mathematical preliminaries. For continuum mechanics. And the associated calculus. Then we looked at linearization. In terms of the directional derivative. So this is important in computations. Then in order, we had the kinematics, where we had defined the deformation gradient and various strain measures that depend on the deformation gradient. Then we looked at the Lagrangian versus Eulerian description. So then following kinematics, we had a balance laws. So this, we looked at the equilibrium equations, the symmetry of the stress tensor, and then some conservation laws. So here we also looked at the idea of objectivity and objective stress rates. So this, so the mathematical preliminary part is fine. That forms the basis for the entire course. In kinematics, it's all straightforward. Given a deformation mapping, you can define a deformation gradient as this. And from this, you can derive all the kinematic quantities, and there can be some relations between them. And given the velocity field, you can define the velocity gradient, spatial velocity gradient as some L. And from there, you can derive a set of kinematic quantities. So these are all the descriptions of the deformation itself. But correspondingly, we also have force fields associated with every deformed configuration. And these force fields have to obey certain laws, which are the balance laws. So fundamentally, there are 5 balance laws. One is the conservation of mass, linear momentum, angular momentum, the first law of thermodynamics, and the second law of thermodynamics. So the second law is an inequality. First law involves heat and other physical quantities. We are well done with the first 3 balance laws, which is the conservation of mass. In Lagrangian description, it is just rho times J is a constant. because J relates infinitesimal volumes to infinitesimal deformed volumes. Rho is the current density. This has to be rho times J should be a constant, which is equal to rho naught J naught. Right. Then the second balance law is this, which is under static conditions. This is the equilibrium equation, and the Cauchy stress tensor is symmetric. This also follows. Then we looked at a concept called objectivity, which says two different observers are equally qualified to describe any physical phenomena. So two observers shouldn't disagree on any a description of a certain phenomena. That is basically objectivity or frame indifference. But then we came up with this idea of objective stress rates. So this is because the material time derivative of this is because the material time derivative of the Cauchy stress is not objective. And therefore, we had various descriptions such as the Truesdale rate, Truesdale rate, the convective stress rate, Yeoman stress rate, and so on. So there are several objective stress rates. Now the next part is put these two together. So we have kinetic quantities which deal with the forces, stresses, and their rates. We have kinematic quantities which deal with the deformation, its gradient, and the time rate of the deformation. Now, next task is to relate these two, and that is basically constitutivity. But in constitutivity, there were some which two kinematic quantities can be related. So we had this requirement of work conjugacy. So the two kinematic quantities that can be related, they have to. So they should be work conjugate, which means the internal virtual power can be written as sigma. So it's sigma integrated over the deformed volume, sigma contracted with d, or the virtual velocity, virtual rate of deformation tensor d. And this is also equal to integrated over the original volume, the first PLR Kirchhoff stress tensor contracted with the rate of the virtual deformation gradient tensor. And this is also equal to integrated over the reference volume, the second PLR Kirchhoff stress tensor contracted with the virtual Green-Lagrange strain rate tensor. And we also, in the exercises, we also looked at other rate quantities such as the Hill. We looked at the Hill strain and other similar quantities, Biot stress, and so on. So following then after constitutivity, what did we do? We had to write down the equilibrium equations. So we said that the equations of equilibrium are non-linear; they are highly non-linear. So we had the concept of linearization. And in in constitutivity, we also looked at hyperelastic materials. Right, we looked at hyperelastic materials, which are those materials in which the stress can be derived from a scalar potential. And that scalar potential is a function only of the strain-like quantity. So that is basically hyperelastic materials. Then we looked at the idea of linearization. Why we need to linearize, and the need for linearization. The linearization is required because our governing equations are all highly nonlinear. So we had to linearize them and then solve. So once you linearize, then finally we saw the concept of discretization. And today we'll be solving it. So last step is solution. So this is the final and the most important step. So to recap, our governing equations are this. right? So this is our static equilibrium, translational equilibrium. We saw that the statement of this, along with the symmetry of the Cauchy stress tensor, is exactly equivalent to stating that the internal virtual work done is equal to the external virtual work done, where external virtual work done is the integrated over the volume T dot del V ds plus integrated over the volume F dot del V dV. So this is the external virtual work done by the system of tractions and body forces on an arbitrary admissible velocity field del V. And what about the internal virtual work done? So the internal virtual work done is given by any of the two, any pair of the work conjugate quantities. So this is given by integral over the volume sigma del d dp, where d is the virtual rate of deformation tensor associated with the virtual velocity field del V. So these two have to be equal for an arbitrary admissible virtual velocity fields del V. So from this point, what did we do? We said this is highly nonlinear because the limits of the integration are dependent on V. So from here we need to get a linearized. We need to linearize it. So this is highly nonlinear in V. So we need to linearize. And linearization, we saw there are two ways of doing it. One is the spatial way, spatial linearization, and the material. Yeah. So we got two expressions for the linearized virtual work expression. One is in spatial representation, and the other was in the Lagrangian or material representation. And we also saw that it is always easier to linearize in the material configuration, material description, and then pull back the expression to the spatial configuration. That is because the limits of the integration are in the Eulerian description. The limits of the integration themselves are dependent on the configuration, right? The current volume depends on the deformation itself because it is a deformed volume. Therefore, that will also enter the differentiation. Since that is not easy, we usually linearize in the Lagrangian description and then push forward all the quantities to the current configuration. So when we linearized it, we got this expression. So the linearization of the internal virtual work done about a point. So you always have to linearize about a certain configuration. Let us call the configuration phi. And the virtual velocity field is del V, right? And in the direction U. So U is a corrective displacement that will get into a Newton-Raphson scheme. Del V is an arbitrary admissible velocity field. And this phi is the current configuration. So this linearization turned out to be for the internal virtual work. It was integrated over the volume del D contracted with. So the C, let me put it in a stylish format. So the C is the spatial elasticity tensor or spatial elasticity tensor acting on the infinitesimal strain associated with U. Okay? You have a integrated over the volume. Plus, you have another contribution, which is sigma contracted with the product of del U transpose del delta V. So this is the linearized expression. Note this del D depends only on delta V. The spatial elasticity tensor depends only on the current configuration. And this is the infinitesimal strain tensor depends only on the displacement U. Here, the stress depends on only on the current configuration phi. This is the gradient of U. This depends only on the displacement U. And this is the virtual velocity. Gradient of the virtual velocity depends only on del V. So this entire term is called the material part. And this is called the stress part. Right? So the linearized internal virtual work expression has two components. One depends only on the material and does not depend on the current stress state directly. And the other component depends only on the current stress state and not on the material properties directly. Right. So we should also linearize the external virtual work done, but that under certain special conditions we saw this is equal to. So the external virtual work done should not depend on the current configuration anyway. It depends only on del V and Q. And this turned out to be zero under certain special conditions where the forces are prescribed. They do not depend on the deformation. And when they are conservative, this was obtained. So the next step we did was discretize these equations. So without spending much more time, I can get directly to the discretized system of equations. So the discretization we basically is we say x is equal to summation a going from 1 to n, where n is the number of nodes, NA of some psi XA. So you express the deformation at any point x as a linear combination of the deformation at some selected points XA. So this is for the deformation. Similarly, for the velocity, the virtual velocity, we had summation a going from 1 to n, some NA of psi del VA. And for the displacements also can be expressed in a similar format. B going from 1 to n, and B of psi. There's no del, it's just UV. Right? So yeah, so this summation, so when we linearize the virtual work, we can always take the summation over this. So one contribution of the virtual work is this. So if you look at del W internal, it takes in two arguments. One is the current configuration that is also discretized, but we don't need to look at it right now. And the virtual velocity field. But virtual velocity field, look at only at the NA del VA component. Right, in the direction U, but you can write it as NB UB. So this is the discretized internal virtual work expression. And so what this turns out to be, this you can write. So just substitute in place of, or let me open the previous weeks. Week 11 discretization. Okay, anyway, let's just do it, right? So we have the expression for del W internal phi comma del V is nothing but integral sigma del D dV, right? So we are saying we have said del V is equal to NA del VA. So and which means what is del D? Del D is the symmetric part of gradient of del V. So this is basically half of del V plus del V transpose. But sigma is a symmetric tensor, so we don't need to write the summation. Only the symmetric part will contribute, and the antisymmetric part will cancel out. The contraction of a symmetric and an antisymmetric tensor is 0. So this can just be written as so look at del V. Del V is nothing. Sorry, this is grad del V plus grad del V transpose. So gradient of del V is gradient of this quantity, which is some NB of x del VB. So this does not have any spatial dependence. Only this depends on this. So this becomes, so it is dou by dou xj of del VB ith component NB of NB has this. So the differentiation applies only onto NB. So this is del VB ith component dou NB by dou xj EI tensor EJ. So basically this is del VB tensor producted with the gradient of NB. So plug this into this. So we don't need to symmetrize it because the Cauchy stress tensor is symmetric. Its action on a general tensor, its contraction with the general tensor will return only its contraction with the symmetric part. So this is basically integrated over the volume. Sigma contracted with del VB tensor grad NB dV. This can be simplified further. So this is del W internal, which depends on the current configuration and the del V. But del V we have discretized it as NA del VA is nothing but integral over the volume. I can write it in components form sigma ij del Vi dou. So this is del VA I dou NA by dou xj dV. So this is nothing but integrated over the volume del VA I sigma ij dou Ni by dou xj dV. So this is the volume, this is the velocity. So these are different. So this del VA is a constant that does not depend on the volume. It can come out. It does not depend on the deformed volume. This is prescribed. So this can come out. So it is nothing but del V dot producted with integrated over the volume sigma acting on grad N A. So the del VA dot sigma. So this is sigma ij. Something with a j index. So it is sigma acting on this vector Na and dV. So this is the expression for the internal virtual work. So this is the expression for the internal virtual work. Similarly, you also have a discretized expression for the external virtual work, and that does not depend on the current configuration. It depends only on the velocity field, which has been discretized as del VA Na. And this will also be some del VA dot some force type for force term. So putting these things together, we get del W is equal to del W internal minus del W external. This has to be equal to 0. So we get it is del VA. Let us call this term as some TA. So you get del VA dot TA, which is a vector. So this is a tensor acting on a vector returns a vector integrated over the volume remains a vector minus del VA dot some. We can call it FA because A index is there. So this is basically del VA dot TA minus FA. This is the residual. This is the residual which has to be forced to 0. And this residual is forced to 0 by some iterative scale. So one thing that we have already seen is the Newton-Raphson. And when Newton-Raphson causes certain issues, the second method is line search. And the third method is arc length. In this week, it was covered. So, okay. So this is fine, right? So this is what we want to force. So del W should be 0 for arbitrary admissible virtual velocity field. There's nothing special about it. So we can take this as 1, 0, 0, 0, 1, 0, and so on. And essentially, it will result in TA minus FA equal to 0 for all the components of this vector TA and FA. So this is the discretized. This is discretized. Discretized virtual work expression. Right? But this is not enough. We also need to linearize it. So if you recall, when we linearized it, we had. So the linearized virtual work expression is as follows. It is d del W internal at a configuration with respect to virtual velocity field del V in the direction U is nothing but, as I just wrote, is integrated over the current volume, the virtual rate of deformation tensor, spatial elasticity tensor acting on the infinitesimal strain tensor, plus integral sigma contracted with del U transpose del V. So these are, yeah. So this is a vector, gradient of a vector is a tensor. Tensor multiplied with tensor is another tensor. That is contracted with sigma, so it returns a scalar. So this is fine, right? Then when we linear, again, we have to discretize it. So we have U is discretized as some NB UB, summation over B going from 1 to the number of nodes. Del V is discretized as some summation going from A1 to N, NA del VA. So NA and NB are scalars. UB is basically the vector of displacements at the node B, and del VA is the vector of virtual velocity at node A. So this was done in the last session. So let me skip directly to the final expression for the virtual internal linearized and discretized virtual internal work. Right? So D is the linearization. This NAVA is the discretization. So the discretized linearized virtual internal work takes this form. It is phi comma NA del VA in the direction NB UB is this expression, right? So this has a there is one component which comes from the material part, and that is this integral over the volume. So this del V. So remember, del V is the virtual velocity. It has to be linear in it because it's a dot product of some residual and the virtual velocity field. So this can come out as del VA dot here we have, so del D is the symmetrization of the gradient. So we can write this as del VA tensor product with the gradient of NA. Again, there is another plus transpose of this divided by 2, but C is also, this fourth order tensor is also symmetric. So we don't need to do that. Contracted with C, contracted with, here it is UB tensor product with the gradient of NB dV. So this is the stress part. Sorry, this is the material part, and you also have the stress part. So the stress part, and this, right, so there's no del VA here. Yeah. Plus we have the stress part, which is it is UB, it is sigma contracted with UB tensor grad NB transpose multiplied with VA tensor grad NA. So this is the discretized, linearized internal virtual work expression. And in components form, this is very simple. So in components form, this is del W internal phi NA del VA in the direction NB UB is so once we discretize, once we substitute this, simplify these expressions, we get to a point where this can be written as a product of two terms, which is the first one of that is del VA dot KAB material acting on UB plus you have the second term del VA dot KAB sigma acting on UB. So this is called the material tangent stiffness matrix. The material component of tangent stiffness matrix. And this is the stress stiffening matrix. So the components are given as KAB C. The ijth components are as follows. So this just follows from this. So here we have a tensor contracted with another tensor, and C is a fourth order tensor. So the ijth component is given as just so the okay. So the ijth component of the material tangent stiffness matrix is given as integral over the volume dou Na by dou x maybe k C IKLJ dou NB by dou xk dV. And for the stress stiffening matrix, so if you look at the stress stiffening matrix, its ijth component is given as integrated over the volume dou Na by dou xk sigma KL dou NB by dou XL dV. But if you look at it, K and L both are fully contracted. So this is a scalar, which means to every and if you write it in a more concise format, this is equal to del VA dot Kc plus K sigma times, so there's an AB, right? UB. So this together, so to every component of this, you are adding a constant. So this, that's a delta Ig. Right, so this is the final linearized, discretized expressions of the virtual work. So the stiffness matrix, the tangent stiffness matrix at any point has two components, one that is coming from the material, and that is computed this way, where C is the spatial elasticity tensor, and one coming from the stresses, and that has got this form. Only the stress enters it, the material components, material properties do not enter the this expression. Okay, so
Naresh,
yes,
the first part I'm getting,
okay,
because for example, in general, we are defining one linear elastic problem regarding any beam or any column or any 1D element. And for that, we are just writing the first component, the material
yes,
component of tangent stiffness. Okay. So the
yes,
first part I'm getting, this is due to some material property, Young's
yes,
modulus, or the
yes,
second one, because
hmm,
actually what I am doing in my current job profile, I'm doing
hmm,
so much simulation work actually.
okay,
So there in the software, just like you know ANSYS, Abacus, LS Dyna, or these type of
yes,
softwares, stress stiffening word is used when we enter in nonlinear continuum mechanics in FEA.
yeah,
There also.
yeah,
So what is the means formulation? I got the clarity, but if we
okay.
want to get the physical significance of this stress stiffening,
Hmm.
what is the physical meaning of this one?
Right. So physical significance, maybe I can take a 1D example and show what stress stiffening is. For example, you take, suppose we have a bar, some, yeah, I think bar is a good example. So suppose just take a bar and say it has got 2 degrees of freedom. Right? Bar usually has only one, but say the vertical displacements are large. So let's just take a bar, two nodes, say
Mm-hmm.
U1, V1, U2, V2.
Mm-hmm.
And after deformation, it takes up some shape like this. And when we consider non-linearities, we always say that the forces are acting in the deformed configuration. So we have force F1, F2, and sorry, say F1x, F1y, F2x, and F2y.
Mm-hmm.
Now, so by equilibrium, we know F1x has to be equal to minus F2x. But if you see,
Okay.
this will not keep the bar in equilibrium, right? So this cannot keep it in equilibrium because uh, these two are separate. When F2y and F1y and F2y are equal to 0, this in general has a lever arm. So you will have equal and opposite forces separated by some distance. So now if you write down the full expression for uh, the virtual work done, so this will be, you have an infinitesimal. So this was the full bar. Suppose you take some infinitesimal element which is going to some other position. The work done by the forces will also be on. So let me say, suppose initially it is ds naught, it goes to ds. So this ds will be, say, uh, this x goes to x plus u. This point goes, so this will be x plus u. Vertically, it will be some y plus b. And this point will go to some x plus u plus du by dx, and y will go to y plus, sorry, this goes to x plus dx, right? So this initially it's x plus dx, and y will go to y plus b plus dv by dx uh, dx. So if you take the forces and write down the virtual work expression, the forces, suppose they stay constant during the process, they will also do some work on this component, which is arising from the so So when the strains are small, you can say the change in length is just you can just subtract the x components and say the change in length is just du by dx. Right? This is the change in length, and you divide it by dx, you get some strain. But when you have large deformation, you have a y displacement, and corresponding to that, you have a stretch, right? So the actual change in length will be some ds minus ds naught by ds naught. So in this ds, you will have some, you will have these things entering into your strain expression. So this dv by dx will also enter your strain expression. As a result, what will happen is that this the net so then if you write down the expression for stiffness matrix, for example, if you so say initially it is subjected to some stress sigma, and then it has stretched significantly, and it is still subjected to some stress sigma only. A part of the so this you think of as a truss element. Part of this resistance to vertical deflection also comes from the fact that this is stretching. So if you just consider linear elastic, if you just consider linear displacements, only the projection will matter, and this will develop no vertical resistance. Okay, or even simpler, let me just take let's just put 3 nodes subjected to some force P, and say it is a truss. After deforming, it takes up some shape like this. Now, if you just do a linear analysis, we'll say this at this point there will be no resistance to vertical load, because if the material stiffness is just you'll get AE by L, A minus AE by L, and so on. So if we don't consider this okay, so suppose you have P. It's like you stretch a rope between 2 points, and then you hang something from the rope, right? So that is what this is. The stiffness in the rope comes from, so this is an axial force member. Basically, this is an axial force member. If you look at in a linear elastic sense, it's not possible to keep it in equilibrium, because you have forces acting upwards at both the points, and this is really not possible. It's not possible to keep it in equilibrium when the member is horizontal. So this is an axial force member. This is also an axial force member, but you have to resist a vertical force P at this point. So you have to resist, the net force has to be upwards on this joint. But that is not possible if you have it. But the actual reason why you have any stiffness at all is because this is stretching, and that stretching comes from this thing. It's because in nonlinearity, you don't ignore this component. So the strains are defined such that it is change in length by original length. And while calculating the change in length, you consider the vertical deflections also, and you establish the equilibrium in the deformed configuration. So, so what happens is the stresses, when they are in the deformed configuration, they are in a different orientation. So they are in a different orientation. And this is what gives rise to stiffness of this structure. So this is a structure where the elastic stiffness, the vertical resistance, elastic part will be 0, and it comes purely from a geometric thing. So if you pull it, or even better, if you just if you take a cable and then pull it with some tension and then arrest the ends, right? You just arrest the ends of the cable. So it is under some tension. Suppose the cable's EI is very small, right? So the cable is something like, the thickness of the cable can be some less than the length by 100. Right now, if you apply a vertical force here, this will obviously deflect. But for if you just treat the beam theory here, right? If you just look at it as a beam theory kind of thing, the deflection for this will be of the order of L cube by T cube, right? Which means you'll L cube by T cube multiplying some constant. When T is less than L by 100, you will have deflection of 10 power 6, which is junk. But in reality, that doesn't happen. If you say, for example, you tie your rope to hang your clothes, you apply some initial stress, and then when you hang the rope, the deflection is something very small. It is of the order of it's of the order of some L by 15 or L by 20, right? Not more than that. It's very small. So if, it's not even L by 20, it's L by 200 or something usually. So that is the physical contribution of the second part of the matrix. So when you consider nonlinearities, so it's like when you have nonlinearities, you have equilibrium. One factor is equilibrium is in the deformed configuration. Equilibrium in the deformed configuration. And the second factor is the displacements in the, so for a bar, this is for a bar. Equilibrium in deformed configuration is always, but if you consider a bar, either this example or this stretched bar example, the strains are the strain is due to both the components of displacement. So therefore, you have if you have a stress that is initially acting, that will give rise to some. So in this case, suppose you're applying a force P, concentrated force P. You take the equilibrium, the deformed configuration, you have something like this. You have T here, and P here. So in a continuum setting, how do you take care of this T? You are discretizing the solid with like 2D or 3D elements. In, in that case, it's not as simple as this. In fact, if you write down the expression, if you write down the full expression for stiffness here, you will have one contribution that is something like EI by L cube something. Plus, you'll have something that comes from T. So in this case, it is just if it deflects by say delta, and say delta is very small compared to L. So this will be some theta, which is roughly delta by L. In that case, your the vertical component will be sine theta, which is also you can approximate it to theta. So this P will be 2 times T delta by L. So if you look at this, the vertical resistance is coming only from 2T by L, right? So 2T by L is what is contributing to the vertical resistance. And you see now where the stiffness matrix. So this sigma, it is linear in sigma, so that is linear in T. And you will have 1 by L coming there. That's okay. Yeah, and delta is the deflection. So delta is the deflection, and delta is the deflection gets here. So this is the incremental displacement. So if you look only at this component, so the virtual work done by this P will be what? Okay, actually this is a good example. So you have this. Okay, you apply a force P here. You can look at it in two ways. One, it will have its beam resistance, and suppose it is carrying some initial tension T. You have so first treat it as a beam, linear, elastic, and so on. So you get I think it's the deflection due to midpoint load will be some PL cube by 48 EI.
Yeah.
This is what you will get. But if suppose so, which means if you have say delta linear, so in this case your P will have one component which is coming from the shear force, right? So this is basically the shear force. If you cut it there will be a shear force on this section, and that is going to resist P. So this here will have V, something like this. So this V will resist the applied P, and that will be one component which is coming from the shear force. That will be delta L EI into 48 by L cube. But this means you will have a very large displacement delta L. So this is one thing. So this I'll not call it as P. I'll call it as the shear force, the jump in shear force or whatever. Then the other component is suppose you move it by delta. This is the other component. So this is when you have no tension. But when you have a tension, the tension is at some angle. This angle roughly I can put it as some delta by L. If it is when the deflections are small. And at this point, I'm also having an applied downward force of P. And this is symmetric, so the other side you have T. Horizontal forces are all balanced. So if you look at the total P, so this is coming from the tension part. So the total P at that point will have one resistance coming from the tension and another resistance coming from the shear force. So one will be from the shear force or the shear force jump, and the other one will be coming from the tension. So from the shear force you have, it is V, which is the jump in shear force, right? You will have some jump in shear force, and the jump should be equal to the applied force P. So this P will have one component which is delta times EI by L cube, 48 EI by L cube, plus another component which is delta by L, 2T delta by L. So this is 2T delta by L. Now this is our KAB material. And this, if you rearrange a little bit, this you can write it as 2T by L, 2T by L delta. And this is nothing but your KAB sigma in this simple case. So this, but in a general case, so this, when you have a very large pre-tension, you can solve it. But what happens if I say I'm starting with zero tension? And as the beam deforms, it will develop some tension and it will have this. In that case, the tension itself depends on delta, and we really don't know. So that is where the nonlinearity comes from. So you can solve this at different stages. One, no effects, no nonlinear effects. No nonlinear effects will give a junk displacement of PL cube by 48 EI. And this is of the order L cube by H cube. So if L by H is something like 100, this will give you some junk. So one small correction you can do is have a large pretension like our cables. Then you apply a P. In case you ignore this, you have something that is proportional to the initially applied stress. So this is the stress stiffening. This is called stress stiffening or stress stiffness. Then, but this is an approximation that you're applying a T initially and you're leaving it as it is. But as the beam is deforming, it will develop some T. That is what happens with our ropes. Like what you type. If you have some high tension cables for transmitting power, that may be pre-tension. But if you tie a rope between 2 points and then you hang a cloth here, you don't have a very high tension. So there the tension develops due to the action of vertical load. And there the T itself is a function of delta. So it's a nonlinear problem. There it's a highly nonlinear problem in delta and this thing. So there, if you want to get a P delta relation, that will look something like this probably. So yeah. So one part from the material is fixed. That is just E depends only on E or sigma Y and other things. And there is one part that comes from the stress. And why it comes from the stress? It's because equilibrium, the deformed configuration, and vertical displacements affect stretch of the fibers.
Okay.
Yeah.
So basically, can I directly say that this stress component
Yes.
of stiffness is just directly related to the geometric nonlinearity?
Yes, this is coming from the geometric knowledge.
Okay, okay, okay.
Yes.
Okay, clear it is.
Okay. Okay. So at this stage, the equation we have is this one. So we have the virtual velocity field dot producted with internal virtual work minus this one, and this is equal to 0, and this we call as the residual. This is the residual. So we want to force this residual to go to 0. So what do? We take a trial phi k, and you say the correct solution is phi k plus some displacement. So we want this r of phi k plus u to go to 0. And this can be expanded in a Taylor series as r of phi k plus some gradient of this evaluated at phi k. No, I don't have to be so. So this plus the directional derivative of r of phi k in the direction u plus some higher order term should be equal to 0. Now this can be written as what? This we just got it as KAB or AB I'll drop. It is KC plus K sigma times U. So this is the linearization of the residual. But what is the residual? Residual is the difference in forces, internal virtual work and this is the internal. When you dot it with the virtual velocity field, it is the difference between the internal virtual work done and the external virtual work done. And when we linearize it, we get something like this: dr phi k u. This is the directional derivative of the residual in the direction u. And this we already saw that if we linearize the virtual work expression, we get some del V A dot Kc plus Ka K sigma u. So del V A dot we have taken out. So this directional derivative of the residual in the direction u is nothing but Kc plus K sigma u. So what we need to solve for, so then we can set up, so drop the higher order terms and set up an iterative scheme. So that is the Newton-Raphson iteration, where we get so drop these terms, take Rk to the right hand side. So you say, so initialize, so have an initial guess phi 0. Then you compute the initial residual R of phi 0, right? Then get into some iterations. Right. So you have to do as long as the residual is some right iteration. So it's like, if I write a pseudo code, it's like do while the residual in the current step, as long as it's greater than or equal to some tolerance multiplied by the initial residual. So let's call it R naught. So as long as the relative error in the residual, right, the forced residual is greater than some tolerance, keep doing something. Keep doing what? So have this. So keep doing something. So what are we doing? The equation that we need to solve for is this. So solve for Kc plus K sigma u is equal to R of phi k. So get u from this expression and then update. Then update the current configuration as phi k plus 1 is equal to phi k plus u. So in these two steps, okay, first step is always find k as Kc plus K sigma. And once you get, so K is equal to Kc of the current configuration, and K sigma is K sigma of the current configuration. And use those two in computing the tangent stiffness K. Then solve this linear equation. So there's a linearized virtual work expression. From there, you can solve for the incremental displacement. So this is coming from the linearized virtual work expression. And then you can update, once you get the incremental displacement, update the current configuration as phi k plus 1 is equal to phi k plus q. But this is not enough. You have to recompute everything else. Now that this is the current configuration, now we can update. So remember our equation is t minus f equal to 0 is what we want to satisfy. So then as a next step, we can update t f sigma, because sigma gets into calculating k, everything as a function of phi k plus 1. Then the next step is compute the residual r as r of phi k plus 1. So at this stage, you will go back here, check whether r of phi k, now k has become k plus 1. Now check if it has converged. If it is not converged, then find the tangent stiffness matrix, the elastic part and the stress part, invert it to get the incremental displacement. Once you get the incremental displacement, update the current configuration. Once the configuration is updated, you have to do this one. So this is coming from the linearized virtual work expression. This is coming from the non-linear, the actual virtual work. So this is virtual work expression. So this is basically the Newton-Raphson iteration, and this is the most fundamental one of the three. So sometimes Newton-Raphson may not converge, it may diverge, or it may converge slowly. In that case, an improvement to Newton-Raphson is suggested as a line search algorithm, where everything else in the Newton-Raphson remains the same. Only difference is that this, instead of making an update as phi k equal to phi k plus u, you make the update as phi k plus 1 is phi k plus some gamma times u. So this is a scalar. So these are all vectors. These are all vectors. This is a scalar. So this scalar belongs to some 0 to 1, say, right, 0 to 1. So so the idea is, so in Newton-Raphson, what we do, suppose we are solving a nonlinear problem like this, and this is the actual response we need to get. And suppose force is specified. Suppose the force is specified. See, this is U and this is F. So we start with some known, so F equal to 0 is a known configuration. So in the first step, what you're finding, we're calculating the tangent, right? So it will have a material component and a stress defining component. So say this is the tangent. We draw a tangent, and then what we are doing, we are finding the okay, we start with that phi, drop a tangent, and then find the force residual. So with this, uh, so with this tangent, you see, so this point, this will be a force residual. But this is the point where residual is equal to 0 and F internal is equal to F external. So so what we do is we at a point we draw a tangent, find the force residual, and see what should be the um, increment, right? So this is the increment. Sorry, this is the residual in the previous step. So this is sorry, this is the full residual. So this is the tangent. So this is the increment U in the first step, right? In the next step, this is the point where we are at. So draw a tangent here. And what is the residual? Residual is so much. Residual is so much. And then make this as this. So you invert it. This will be what U2. This is the increment we get in the second iteration. But corresponding to second iteration increment, you get. So going from here to here is the update, the stress update. Similarly, going from here to here is the update. Finding this is the invert. This part is inverting and finding the tangent. Sorry, increment. So you reach here. Then again draw a tangent, and we slowly converge to this point. But what happens? But an improvement to that is line search, where you don't increase to the full extent. So in a 1D case, it's very trivial. But these are all vectors in general. So the improvement is you treat U as a direction in which you have to move, but you don't need to move fully. That is the idea. So this is because this is done to keep the this displacement within the radius of convergence of this Newton-Raphson iterations. Because if the displacement increment is very big, the solution may diverge. The iterations may not converge. It can go to somewhere else. So you keep a constant gamma and find the constant such that at that point the residual is orthogonal to the increment. Right. So this is an improvement. Introduce another parameter gamma, which is a scalar, and the update is phi k plus 1 is equal to phi k plus gamma u. And if we have a scalar which is an unknown, we need an extra equation. So that extra condition comes from r of pk plus 1 is orthogonal to u. So u is the direction in which you are going. So u here is a scalar, but in higher dimension problems, it is a vector. So this is the condition that is used. So it's like after we do the update, we get a residual, and at that point the residual is orthogonal to this direction, which means that residual does not have any component in the direction u. So this is basically r of phi k plus gamma u dot u is equal to 0. So we solve this equation and then get gamma. But what is it? This is for every Newton-Raphson iteration. So In the kth step, you need to solve one nonlinear equation. So this is complicated. So if you refer to the slides, there is a quadratic approximation of. There's a quadratic approximation of R. Because this is highly nonlinear. You have a nonlinear equation at every step of a nonlinear root solving algorithm. So that is not meaningful. Therefore, choose this gamma by solving not the actual nonlinear expression. Instead, you approximate this R by a quadratic term. Right? Approximate the R by a quadratic. This entire thing by a quadratic polynomial. Then you can find gamma that satisfies that quadratic polynomial. Okay, so the last,
Naresh, in the last
yes,
slide, the step that you just told that we have to get the value of this linearized
gamma,
constant gamma.
yeah,
So basically, for example, we are getting any FEA problem to do some linearized iterations. Okay.
okay.
So for that problem, is it necessary that we have to start with the uh, general, or we can say full Newton-Raphson method, or directly we can jump to this line search method?
No. So line search, if you see, this is one step of Newton-Raphson, right? So this is one step of Newton-Raphson. Phi k plus 1 equal to phi k plus gamma u is one step. But within that step, there is a, if you just have phi k plus u, you get u as k inverse r minus k inverse r. So this is just one step solving. This is a linear, this is a linear thing, linear equation, which can be solved easily. And this is just an update that can be, that is Newton-Raphson. Now in this, inside the Newton-Raphson iterations, you're introducing one unknown gamma. So what it says is, instead of going the full distance along u, just go a gamma. Right, just go to a fraction of that, and this gamma can be either positive or negative. There's no, just go to a fraction of it. Then you have to solve for gamma in every step of Newton-Raphson. So in a nonlinear FEA problem, so you should always start with the Newton-Raphson this thing. So if you have a problem like this, if you have some externally applied forces, any problem, you can put it in this format. F external is F internal plus. If this turns out to be KU, it's a linear problem, but otherwise it's a nonlinear problem. So you linearize it, get residual as a function of u, then set up a Newton-Raphson iteration. So do as long as the residual is greater than some tolerance. Then you have the first thing, you find k as the find k of u. Then get this. Then you try to get this update, right? So you try to get u as k inverse minus k inverse r. That is also okay. In the next step, instead of updating the current configuration as x plus u, say xk plus 1 is xk plus u, you move only a fraction along the distance, which is gamma. But we don't know this gamma, so what you are doing is find gamma from this condition. Find gamma from this r of xk plus gamma u dot product with u equal to 0. So this is one equation, right? So solve this equation, get gamma, and after you get that gamma, do this update, then go to the update step. In the update step, you redo what is f internal of xk plus 1, r of xk plus 1, and check if this r of xk plus 1 is within the tolerance, otherwise go this. So this line search is a variant of the Newton-Raphson, where inside the Newton-Raphson, you're solving another equation to find how much you have to move along the tangent direction. So you get a tangent. In Newton-Raphson, you invert the tangent with the full this thing and go here. But in line search, you don't go to the full extent. You just you get a tangent, but in that direction you go only to some distance, and from there you take another tangent. That is what we do.
Okay, okay. Okay.
So yeah,
No,
so you should start.
actually, this thing I know, what you have explained here, this thing I know.
Uh,
But I want to ask,
uh,
for example, initially we don't
uh,
know that
uh,
whether my solution will be converged or not. So
okay.
for that, I have to start with the full Newton-Raphson method, or we can say conventional Newton-Raphson method. And
Oh,
in
okay.
that particular, if I am finding that this solution is not going to be converged, then I will start to doing this.
Hello.
Hello, hello.
Hello. Yes, yes. Sorry, there was a. Uh, yeah, we should start with the conventional Newton-Raphson, or
And after that, if we are getting that our solution is not going to be converged, then we have to do this
okay.
thing.
You can do that. So yeah, that we can see. So suppose it's taking too many iterations, or if it is very slow, you can
Mm-hmm.
try this. You can try this line search. Right? That is
Okay.
one alternative in case the increments are so big and the new solution seems to be diverging.
Mm-hmm.
Even better than line search, one thing is you can reduce the increments. So you know that you don't apply the full external force in one step. You apply it in small steps, right?
Okay.
So when I do these things, we just bring down these increments to a very small size. So when you decrease the force increment size, usually they'll start converging. There's no big issue. This line search is very expensive in general. So I would
Mm-hmm.
say first, if you are using full Newton-Raphson, which is where you use the correct tangents, bringing down the force increment size may help more than the
Mm-hmm.
line search.
Okay.
Uh, then even in that case, if it is not converging, then you can look for a line search. But even if you mm, even if you do line search, if you have limit points like this, at this point it will not converge. Newton-Raphson will not converge. It will jump to some other point. So
Okay.
uh, yeah, so I'm not really. So line search algorithm gets a benefit when you use modified Newton. So instead of using the exact tangent, if you use some approximation to the tangent, that in that case line search helps. Because
Okay.
in Newton-Raphson, finding the tangent itself is a costly step. And once you have
Mm-hmm.
found the tangent, doing another iteration every step will make it extremely costly, and it's not going to help with the computation cost. If you want to do it faster, make the tangent approximate and make the line search accurate. Approximate tangent with this line search, uh, will perform well. You'll get benefits in the computational time. If you use exact tangent and line search, it's not going to be very different from uh, Newton-Raphson with a reduced this time load step.
Okay. Okay.
Yeah.
Okay. Get it. Okay. Got it.
Uh, uh, yeah. So the last thing, so what I said in the last slide was just if we have limit points in the response, and this is a 1D case, but in general, we can have limit points in the response where you have so here if you say the tangent to the curve at this point is flat. The tangent to the curve at this point is flat. So it will not meet anywhere. So that if the tangent, so it's not invertible basically. So the tangent is 0. So we cannot really solve for ku is equal to minus r. This cannot be solved. Therefore, Newton-Raphson breaks down. So if we land at a point where the tangent is 0 in 1D case, or uh, in the multiple dimensions, if we land at a point where the tangent stiffness matrix Kc plus K sigma is not invertible, then Newton-Raphson actually breaks down. So in those cases, what we do is instead of going by instead of taking the increments in the force, instead of making the force increments predetermined, right? So here we force increments are something that we are predetermining, and then we are finding the solution for a specified increment of force. Instead of that, what the arc length method does is you can express the force itself as some load factor times a known force. So this is a known force vector. And this is a scalar. So the scalar can take some values from 0 to whatever, 2 or 3 or whatever it is. So a maximum. So when it is 0, it is unloaded. The structure or solid is unloaded. As we take it to some point, it has some force. So and it is proportional loading. Okay? This is proportional loading. All the components of the force are increasing at the same rate. So this is proportional loading, and this is the load factor. So in the arc length method, instead of keeping the force as as a known thing, as a predetermined thing, you can find you can also keep a fraction of the force as unknown. But the price we pay there is we need additional conditions. So again, as in the line search also, we had an additional scalar, but that is only for the displacement. And inside the Newton-Raphson, we had to do some. We needed an additional condition to solve for this. Similarly, in the arc length method, there's an additional scalar lambda, and we want some constraint for this for getting this lambda uniquely, right? So this is some addition. This is also going to be determined by the method in every iteration. So how do we do it, right? So again, our nonlinear equation is r of some xk comma. So lambda also varies with every step. Say lambda k. So xk plus 1 comma lambda k plus 1 should be equal to 0. So we want to force the residual at the k plus 1 step to 0. But again, so this you can expand it in Taylor series. So it's a multivariate Taylor series. So it's r of xk comma lambda k plus, with respect to xk, what do we have? It is dr xk comma lambda k in the direction u, plus then you differentiate with respect to lambda k, which is dou r by dou lambda. Let us say delta lambda. Lambda k plus 1 is delta lambda plus lambda k. And higher order terms is equal to 0. So this is just r. So this is just r of xk comma lambda k. Plus this will be, as we know, it is just the tangent stiffness matrix times u. And you have something else. So what is del r by del lambda? We'll see what it is. So r is f internal minus f external, and f internal is whatever it is. It depends only on x. If it depends only on the current configuration x, and f external is, we saw it is lambda times f bar. So dou r by dou lambda is what? This will not depend on lambda. The internal is not going to depend on lambda. So it's only minus f bar. So this one is just minus f bar times delta lambda, and this is equal to 0. So this is the equation we'll be solving for. So we need to find u as well as lambda. R is known. R depends on the previous step values xk and lambda k. So r is known. K is known from the previous step value. So the equation that we need to solve for is r of xk comma lambda k plus k, which is obtained from the previous step, times u minus f bar times delta lambda is equal to 0. We have two unknowns and one equation. So yeah, this is a vector equation, but this is like n cross 1 vector, n cross n matrix. And in addition, you have one unknown variable. So to find this unknown variable, we have something called the constraint expression. So we have a constraint. We call something called the constraint surface. And what the constraint surface does is you restrict the, suppose the issue was we could not find a tangent here. The tangent to this curve at this point is actually 0, and we cannot invert it. Instead, what we can do is, if we get to this point, say we get to this point, about this point, you construct a surface and see where the surface is intersecting this FT curve. So instead of going along the same curve, so initially we were going like this, we went like this. Instead of going along this curve, go along this constraint curve. So take a constraint surface, and this. So in this case, the load is actually decreasing. If you monotonically increase the load, we cannot get a converged solution here. But here we actually have a decrease in the load. So this is our delta lambda, and this is what? This is delta u, or this is u basically. So have a constraint surface in this form, which is I can say make both of these unknowns. So define a new vector S, which has u as well as some delta lambda times f, and you put a phi. Phi is just for, this is a force quantity, this is a displacement quantity, just for the dimensional consistency, you put a phi. So phi can be just 1, it's not important. So one choice is you can use the simplest case where this is a circle. S dot S is some, let me just use R square. Let me just say it is some constant. Say some C square. So this radius is C. So this is an additional condition on lambda and u. So so that's it. Then all we have to do is solve, right? So this is again very similar to the Newton-Raphson. The update step is the same. Xk plus 1 is xk plus u. Similarly, but here we are not only updating the displacements, but you're also updating the load. Lambda k plus 1 is lambda k plus delta lambda. Now we have to find u and delta lambda. How do we find u? For both of them together, we have one expression, which is r of xk comma lambda k plus k of xk, tangent computed from the previous step, acting on the displacement, minus f bar delta lambda is equal to 0. So this is a scalar, this is a vector, and yeah. So one trick is you can split the u into two components. You have one u1 which satisfies the force residual, and another part which is proportional to this delta lambda and u2. So say, and it is such that r minus r is equal to k u1, and minus f is equal to or f is equal to f bar is equal to ku2. So these two components of the displacement can be solved independently, right? So once we do that, we get r of xk comma lambda k, and this will split into two parts. One is k of xk u1 plus delta lambda k of xk u2 minus f bar delta lambda is equal to 0. So this is 0, and this is also automatically 0 if you take delta lambda commonly out. So one issue is solved. U can be split into two components. Therefore, we get a U that actually satisfies this equation. But U is also dependent on delta lambda. Now we just have to find. We just have to substitute this form of U into. So so what we have done, U is an unknown vector. U is an unknown vector. We have expressed this as a sum of two known vectors, where one known vector is u1 is equal to minus k inverse r, and u2 is equal to k inverse f bar. So this u1 will vary with every iteration because r is configuration dependent, but this u2 is a constant. F bar is the externally applied, is a known vector. So this k inverse f u2 is going to be a constant. So we have split u into two components. U is an unknown vector. We have written it as a sum of two known vectors and an unknown scalar delta lambda. For finding this unknown scalar delta lambda, substitute in the constraint equation, constraint surface. So what is the constraint surface? S dot S equal to C square. S is this. So in place of S, so S is U and something. But what is U? U is just U1 plus delta lambda U2. And here we had some phi delta lambda F bar. So what are all unknown in S? U1 is known, U2 is known, F bar is known, phi is known, only delta lambda is unknown. So just, and it's a quadratic, so delta lambda is, yeah. So next step, just solve for this. So we have this constraint S dot S is equal to C square. So what we have is U1 plus delta lambda U2. Okay, actually, sorry. So this constraint is on the step, total step. So there will also be something up to the previous point, right? So there will also be so this delta lambda is the full step. But in every iteration, you have a delta lambda k. So it's like up to the previous iteration, you have some delta lambda k. And delta lambda k plus 1 is delta lambda k plus delta lambda. Similarly, uh, delta u k plus 1 is, or delta, the current configuration, delta x k plus 1 is delta x k plus this u, right? So the sum of all increments up to the previous iteration plus the current increment, that should be equal to 0. So you have a delta xk plus something, and here you have a delta, yeah, you have plus phi delta lambda k f bar. So this is a vector, this is a vector, and so this is a 2n cross 1 vector, right? So if n is the number of degrees of freedom, corresponding to every n you have a force. So if this is n cross 1, this is n cross 1, the total size is 2n cross 1. Take the dot product and set it equal to c square. So this is a quadratic equation in delta lambda. So you get some expression as some c1 times delta lambda square plus c2 times delta lambda plus c3 equal to 0. So you can solve for c1, c2, c3. Therefore, you get delta lambda. Once you get delta lambda, get u as u1 plus delta lambda u2. And then once you get u, update the configuration. Xk plus 1 is xk plus u. Then once you get the configuration, get the residual and check if the residual has converged. So Newton-Raphson is the base. When you don't take the full increment, you just take the increment as a direction and take partial steps, that is line search. And arc length is when you have cases where this k can be singular. Yeah, when you have cases where this k can be singular, don't work with load increments. Instead, work with these instead work with the increments in along the arc length. That is, keep delta lambda, keep the load increments also as an unknown. For example, in this case, when you hit the limit point, what happens? When we hit the limit point, at this point, the k will become singular. So this ku will actually disappear from the equation. But you can still find the delta lambda such that it is intersecting with the curve here. So what happens here is, so this is why it works. So what we have is r plus ku plus minus delta lambda f bar is equal to 0. This is our internal virtual work, internal force equal to external force expression. And suppose we hit the point, suppose we hit the limit point. Suppose we hit this limit point. Here, the tangent stiffness matrix is singular. So if tangent stiffness matrix is singular, then you may have this Ku may not be invertible. So you can have multiple solutions. That is one thing. So you can so this K so you have this K U1 plus delta lambda U2. This itself we cannot find U1. Basically, you cannot find a unique U1, but that is not a problem. If we can't find a unique U1, say it is take it as 0, right? Take it as 0. Therefore, this K acting on 0, this part will vanish. So we'll be left with R plus delta lambda K U2 minus delta lambda F bar equal to 0. But so this here what we have is we'll only so so we cannot find a tangent and move to the next point on the curve, but instead you satisfy the constraint equation with this choice of delta lambda. So you try to satisfy the constraint equation, and when we solve the constraint equation, we'll get a delta lambda which is negative. So you will see that delta lambda, you will actually have to reduce the load to get the next equilibrium point on the curve. So that is the idea. So instead of always increasing the force in some known fashion, we find the increment. So this can be less than 0. So if we want to be able to solve for it, you find the next load increment cannot be there. The next load has to be decreased. And once you have a load decrease, you can find you can redo the entire thing. You can once you have the load decrease, you can trace the equilibrium curve. So yeah, that is the idea of this arc length method. Okay, so let me. Okay, so let us solve some problems. So if you see, there is a slide, something incorrect in the solution. One of the students pointed out. So there is something incorrect with the solution in solution of an example problem in the reload it. Yeah. So there is this first example problem. You are given two nonlinear equations. So this is a 2x2 system. So think of it as a finite element. So think of this as an internal force or a force residual term. Let's think of this as an internal force, and this this is the expression for it. So if you have to solve for it, let me say. So I have an R of u, which is a vector, and that is given by this x1 square plus x2 square minus 4, x1 square minus x2 plus 1. Right, so sorry, not R of u, it is R of x. So we want to start with an initial guess xk, and we want R of xk plus u to be equal to 0. This is a basic Newton-Raphson, not the line search. Line search is not required for such simple problems. That is when you have a large number of degrees of freedom, line search may be required. So this is what we want to do. So we say R of x times u is equal to 0. So you say xk plus 1 is equal to xk plus u, where u obeys the above equation. So this is the Newton-Raphson scheme. This defines the Newton-Raphson scheme. And k in this case, k of xk is what? K of xk is so k is something like the gradient, right? So k is this has to be, so this is a differentiation with respect to x1, then x2, and so on. So it's k11 is 2x1, k12 is the first component differentiated with respect to the second variable. So it is 2x2. This is 2x1. This is -1. This is k. So this also matches. So this is all in the kth step. This is the stiffness matrix in the kth step. So this yeah. So and then they have specified a starting point. X0 is 1, 1, 2. So when you solve it, so this first iteration is fine. Second iteration is also fine. In the third iteration, there is something off here. So when I calculated manually, there seems to be something off. One of the students also pointed that out. Sarvesh pointed it out. And but even if there are some mistakes, it will eventually converge. That's the thing about Newton-Raphson. But on the other hand, the problem in the assignment is a little more complicated. That can also be done in hand. But let me just demonstrate it on a code. So you can, or even rather than a code, if you want everything in a tabular form, you can even do it in Excel. Maybe I'll do that. It's easier to use. So just say we have an iteration number. So the things that you need are an iteration number, right? You need an iteration number. Then we want something for the current xk, right? So let's say you have an xk. So this is, if it's a 2D problem, you have the first component and the second component. Then you find r of xk, the first component of, or I'll say r1 of xk. R1 of xk. Then you similarly have an R2 of xk. Then what else is required? You need k11, k12, k21, and k22. Right. So these are fine. Then what we need? We need to invert it. So so we need the determinant of k. So let's say determinant of k. This is one thing. Then say so this up to this point it's fine. So in the first iteration, your xk1 and 2 are given as 1, 2, and r1 is computed as x1 square plus x2 square. So this is x1 square plus x2 square minus 4, and this is x1 square, sorry, x1 square minus x2 square plus 1, and this is 2 times x1. This is 2 times x2. This is 2 times x1, and this is 2 times x2. Sorry, this is just minus 1. So the determinant is k11 star k22 minus k12 star k21. right? So next, what do we do? So once you get the determinant, we have to find the u. So let us say, let's say k inverse, right? So let me call it k inverse 1 1, k inverse 1 2, k inverse 2 1, k inverse 2 2. So k inverse 1 1 is, so you swap the diagonal entries and multiply the other entries by -1. So k inverse 1 1 is equal to k 2 2 divided by the determinant, and 1 2 is minus of k 1 2 divided by the determinant, and this is minus of k 2 1 divided by the determinant, and this is k 1 1. This is k 1 1 divided by the determinant. Now finally we have to multiply this with the negative of the residual and get the u. So you have a u1 and u2. So u1 is equal to k inverse r1 plus this thing, right? So it is minus of, so there's a minus this one star r1 plus 1 2 star this thing, and this is equal to same thing. So I have a minus of 2 1 star r1 plus 2 2 star r2. Okay, so okay, it's not k11 in this thing, right? It's k1 inverse. One star this plus 1 2 star this. This is 2 1 star. So let us see. This is k22 by determinant. Determinant is fine. K12 is what? K12 is 2x1, right? It's not 2x2. 2x2. 2 4 2 minus 1. This is 2x1, 2x2, 2x1 minus 1. Point 1, 0.4, okay. 0.2, 0.2. U1 is 6. Unpaid. So 0.1 times 1. Okay, let us see R. Okay, this is the Schwitz. Yeah, so this is fine. This is the first iteration. So the next iteration, it's just this is equal to this plus u1. and this is equal to this plus u2. This is the second iteration, and all these can be simply dragged down. So you drag it down. So we get R1 as 0.05. So you can compare, right? In iteration 2, R1 is 0.05, R2 is 0.01, K11, K12, K21, K 1.8, 3.6, 1.8 minus 1. Yes, they are right. Then determinant of K is minus 8.28. That is fine. And you have inverse values are fine, but the increment you should get is 0.01039 and 0.0087. The increment we get 0.01039 and 0.0087. So those are also fine. So again, then do the so this is, let's take it to 4 or 5 iterations. Right. So again, update the x1 and x2 values. Right. So x1 and x2 values are updated as 0.8896 and 1.7913. Then update all these. Update all these. And for we want more degree, more digits, right? So let me just make these 9 or 10 digits. Scientific. Yeah. So in the third iteration, you start with 0.8896 and 1.79 as the initial guess, right? So R is one point. So the 0.018,349, and what do they get? So in the third iteration, we get 88961. And 1.79130. R of x2 is 18349 and 0.00010788. So that is what we have here. And the stiffness matrix entries are also matching. 1.779, 3.58 to 1.779221 minus 1. And we have U1 and U2 computed as 0.00699 and 0.001650. So again, having done this, find the next two iterations. So this is an update, and then yeah. So at this stage, it has nearly converged. So even up to 8 figures of, so taking up to 8 figures, we are getting 0. So it's like U1 and U2 updates are in the order of 10 power minus 4. So at this stage, the residual also is something like 1 into 10 power minus 8 and less than that. So this value can be taken as the converged solution, 0.88954362. So solution is 0.88954662 and 1.7913. So that is what we have. Now, for the second problem, yeah, so this is another problem. So here we have a 3x3 system, and yeah, here we have a 3x3 system, and this is going to be a bigger thing to solve in Excel. So I'll demonstrate it on the on Python, and you can do it similarly for the assignment. So for this, as there's a suggestion, write a computer code to solve it. It's better if you do it on a calculator. The number of significant figures will cause some issues, especially when you go to higher iteration counts, right? So this and these are fine. These are just quadratic. That is, the stiffness is linear. Therefore, the force displacement is just quadratic. So it's okay. But still, these are numerical type answers. So it's better you do it on a computer. It's better that you solve this on a computer and input the numbers here. So I'll demonstrate how you do it for this. How we do it for this one. This problem on a computer, because the solution is not given here. And I'll just show this is what we get to. So we have, so suppose, so recall the Newton-Raphson iterations. We need something to start with. So you can use this Google Colab that has it's a free Python, online Python compiler. So you can use this. So let me just call the file name as some Newton-Raphson demo.
Naresh,
Yes.
when we are not given the actual equations in terms
Okay.
of x1, x2, x3, and
Yes.
we are just given as the some physical problem. Okay,
Okay.
so
Okay.
for that type of problem, I think we have to just make the equilibrium equations of the nodes first, and then we have to convert. Then we have to make the f1, f2, or f3, and whatever it is.
Yeah. Yeah. So okay. So this basically, like in this assignment problem, right? You have some.
Yeah.
Yeah, we have some physical system. So there are some springs connected in parallel, and some are in series, and each of them is a nonlinear spring, and you're asked to find some solution to it, right? So I can't solve this, but I can. So in this case, let's just take this. Say you have a multiple degree of freedom system. Say you have one spring, uh, and this is connected to another spring.
Hmm.
Say this is connected to some. Or just put three springs. It's simple. So there's a 2 degree of freedom system. This is the first node. This is the second node. This is K1, K2. No, it's not K1, K2, K3. So this is K1 of U. Or let me do it as, let's say this has a force response F1 of delta, where delta is the extension. This has a force response F2 of delta, and this has a force response F3 of delta. So these are the internal forces. So now you can use any method to arrive at the equilibrium equation. You can start with the internal virtual work and external virtual work also. So that's the easiest actually, if you see. So you see W internal will be F1 dot del V1, where del V1 is this, or here in this case, it's the extension del delta 1 plus F2 dot del delta 2 plus F3 dot del delta 3. And what about the external virtual work? Let me call the external forces as P1 and P2. So that
Yeah.
is P1 dot del V1 plus P2 dot del V2. So V is a virtual displacement, del V1 del T. But what is del delta 1? Del delta 1 is equal to, so we say the virtual velocity field must be admissible. So if it has to be admissible, then this delta 1 has to be calculated from this del. It cannot be independent. So del delta 1 is just delta V1. Del delta 2 is del V2 minus del V1. And del delta 3 is minus del V2, right? So these are something, so corresponding to continuum, this is something like strain displacement relations. So strain displacement relations are nothing but compatibility conditions. So it's something like that, something like strain displacement relations. Substitute in the virtual internal. So del W internal is equal to F1, right? So it is F1 dot del V1 plus F2 dot del V2 minus F2 dot del V1 minus F3 dot del V2. But what is external virtual work? It's P1 dot del V1 plus P2 dot del V2. Now do some rearrangement. So this you can write it as some P dot del V, and this you can write it as del V1 del V2. So this is a row vector. And what is multiplying del V1? It is F1 minus F2. What is multiplying del V2? It is F2 minus F3. So our virtual work expression is del W is equal to, you get a del V. So this is a matrix dot with internal. So internal is F1 minus F2, F2 minus F3 minus P1, P2. This is the external. This is equal to 0. So this is basically what we have. We have an arbitrary virtual velocity field dot product with some residual. So this is our residual. This is our residual. So what is R of U, R of X? So now the problem is F1 is some F1 of delta, and delta itself is coming from the current configuration, right? So F1 is some F1 of delta, and therefore F1 is a function of some. So this will get in. So delta is nothing but U1. So it is F1 of U1, and F2 is F2 of U1 and U2, and F3 is F3 of U2. So this is internal forces. This is the vector of external forces. This residual has to be forced to 0. So you say R is equal to. So R is a function of U1. These are the real displacements. V is the virtual displacement. U are the real displacements. R of U1 comma U2 is what? It is F1 of. In general, let me just put U tilde, like U vector minus F2 of U vector, F2 of U vector minus F3 of U vector. These are all known functions, right? These are known functions minus P1, P2. This is our residual. Now, what is our stiffness matrix? Stiffness matrix is dou F1 by dou U1 minus dou F2 by dou U1, dou F1 by dou U2 minus dou F2 by dou U2, dou F2 by dou U1 minus dou F2 by dou U2, dou U1. And here it is dou F2 minus F3. Sorry, this is F3. Dou F2 by dou U2 minus dou F2 by dou U3. This is the this is the internal this thing, and this will contribute to 0. So this will be 0. This will not contribute. So again, as usual, you want to set R of some guess. Let us say UK plus delta U equal to 0. So you set R of UK plus K of UK delta U equal to 0, and find the update as minus K inverse R. So we have K is this, K is this, R is this, and you can find minus K inverse R and find this update. Then again, update UK plus 1 is equal to UK plus delta U. So this is what. This one and this one together will form the system. So now it doesn't matter. F1 can be any function of u. For example, I can take F1 is uh, some a times u1 square plus b sine u. And F2 I can write it as some it cannot depend on u. So yeah, it depends on delta 1, and delta 1 is just u1. So F1 is a nonlinear function of delta 1. So it's like F1 can be some a delta 1 square, F2 can be some uh, a delta 2 sine hyperbolic delta 2, and F3 can be some e power cos delta 3, something like this, b power cos. So in place of delta 1, delta 2, delta 3, I have to substitute these in terms of so again, delta 1 is equal to u1, delta 2 is equal to u2 minus u1, delta 3 is equal to minus u2. So these are the real displacements. These are the virtual displacements. Yeah. So for a spring assembly or something like this. Okay, one more thing. If you also look at the final expressions that we are getting, we say P1 is equal to F1 minus F2. That is exactly the same if you say if you take equilibrium of the joint of this body here, right? So you have P1 is equal to F1 minus F2. F1 is in this direction, F2 is in this direction. And similarly, for the other point, you have P2 is equal to F2 minus F3. So that will be, yeah, that's it. So don't, yeah, you can start with the virtual work expression, or you can also start with drawing the free body diagrams of every connection here. Yeah, but the finite element method is take the virtual work, that will give you directly. For discrete systems, you can draw free body diagram, but for a continuous 2-dimensional or 3-dimensional body, virtual work is the way to go. So this is the way. So maybe start, if it is a physical system, start with the virtual work. If it is just a set of equations, start with the R.
Okay.
So let me just quickly solve this problem because this solution is not given in the. We start with, again, you start, they say start with some x naught is equal to, okay, rather first some. So in Python, you need import certain library, say import this NumPy library. It's important. Then you can see they have already given, he has already computed the tangent, so we'll use the tangent. So let's use one function for compute residual. So let's have a function, find compute residual. And what is the residual? Residual is this. So it takes in 3 quantities. Let us just say it takes in the vector x, right? And say x1, x2, x3 are the 3 components, x of 0, x of 1, and x of 2. So what are these? 3x1 minus. So let's say R1 is equal to 3 times x1 minus cos p dot cos x2, x3. So it is x2 star x3 plus a minus half minus 1 by 2. Then R2 is what? R2 is x1 square. So x1 star star 2 minus 81 times x2 plus 0.1 square. So it is x2 plus 0.1 square plus sine x3 plus sine p dot sine x3, then plus 1.06. Okay, then R3 is what? R3 is e power minus x1 x2. So it's np dot exponent of minus x1 star x2 plus 20 x3 plus 20 x3 plus 10 pi minus 3 divided by 3. This is equal to 0. sorry, this yeah, this is the thing. Now what this has to return? This has to return this vector. So let's say np dot array x1, x2, and x3. So this will return this residual, sorry, r1, r2, r3, what I'm r1, r2, r3. Then this is fine. Then let us also code in the tangent stiffness. So def compute tangent. Again, it will take x as the input. Again, let's take these out, x1, x2, x3 out. Now let me just directly code k. What is k? K is this np.array will initialize a matrix, and the first row is 3, yeah, first one differentiate with x1, then you have x3 sin x2 x3, and then you'll have an x2 sin x2. Yeah, so it is 3, minus. So minus cos differentiation is just sign. So it is x2 star x3 star p dot sine x2 star x3. And the third one is x2 star and p dot sine x2 star x3. So this is the first row. Second row is okay. So we can find from here. Why should we look at? So it is 2x1. Then it is x2 dependencies with the 81. So it is 2 star 81 star x2 plus 0.1. There's a minus. So there's a minus 2 star 81 star. So it's yeah, minus 162 x2 plus 1. The third term is with respect differentiate with respect to x3. So R2 dependence on x3 is cos. So it is just np dot cos x3. So this is the second term. So yeah. And the last one, you have in the exponent x1, x2. So first one is just minus x2 star np dot exponent of x1 minus x1 star x2. Then with respect to x2, we have to differentiate. So it is almost the same. In place of x2, we'll have x1 minus x1 star this. And the last, with respect to x3, it is just 20. Right, so minus x2 minus x1 20. Okay, and this is the tangent stiffness. It's the tangent is not the stiffness, it's the tangent, and return k. Okay, so this we have functions for computing the residual and the tangent. So what is the next step? We can write the code. So start with x0 is they are given. So start with the given array 0.1, 0.1, 0.1. What happened? You just reload it. Yeah. So start with the given array. Now first take R0 as the initial residual. So what it is? Compute residual of x0. Then we can use a while loop. While so let's define a tolerance of 10 power minus 8 or 6. Maybe 6 is good. And initially R is also the same as the tolerance. So this is also equal to R. So while the absolute value of R by is less than, while it is not converged, right? So it is greater than, right? While it is not converged, what should we do? So the Newton-Raphson scheme. First step, find the increment. How do we find the increment? So U is equal to, we have to solve, right? So it is K. So for solving a linear system, it is NP dot linear algebra dot solve. So first one should be the matrix. Second one should be the vector. So it is R naught. So R naught is our R naught is our this thing. R naught is our right hand side. A, if suppose you are solving Ax equal to B, K is the matrix and R naught is the residual. So initially, it's not R naught, it's R. Right? At every step you get R. So yeah, here also you can say X naught is equal to X, which is the current iterate, is equal to this. Now, in every iteration, what is the first step? Form the residual. So R is equal to compute residual of X. Okay, we found the residual. Then K is equal to compute tangent of X. We got K and X. Then we solve K R. So there's a minus sign because we want to solve Ku is equal to minus R. So I'll put a minus sign in front of R. Then I update X is equal to X plus U. Right? So this X equal to X plus U. So in the next iteration, what will happen? It will compute R, it will compute K, it will find U, and then check this. So it will keep doing it until this absolute of R is less than this. But it shouldn't run into an uncontrolled loop, or if it is diverging, we need to have a check. So let me have a check. So let me have a check as like, let me have a counter. And in case it is running away into some uncontrolled loop, I'll just, so if say it takes 100 iterations, if KK is greater than 100, break the loop, right? And in every iteration, let me print. So let us say, what is the format they have printed? They have printed K comma X1, X2, X3, and this norm, right? So let us say, let's print X. That's fine. Let's just print X. So this is done. We can run it and see what it does. Okay, truth value of array. So this R is a vector, right? So we have to take some norm. So let me see. Let me just say np dot linear dot norm of R. So if it's a scalar, you can just say R. In other cases, you need to take the norm. So by default, it will take the second norm. Okay, so now let's run it. Compute tangent is not defined. How come? It's defined. Let me run all. Right. So yeah, so these are the values. Let us compare it with the this one. Yeah, so it starts with 0.1, right? Why does it start with? Okay, I'll print an X here. So it's before the iterations, I'll print another X. Print X. Yeah, so it starts with 0.1, 0.1, 0.1. That's given. Oh no. They're asking to start with 0.1, 0.1 minus 0.1. Okay. 0.1, 0.1 minus 0.1. That's a slight difference. Yeah. So how do I put them side by side? Yeah. Right. So Yeah, so 0.1 minus 0.1, then 0.499869 728. Yeah, that's fine. Then 0.019 minus 0.5215. Then 0.5000 something, 0.00158, minus 0.523. Then 5.5 something something something. So this is in scientific notation, but this is in normal number notation. So again, it's 0.50000 something, 0.0012, 0.52. So the first component has already converged. It is 0.50000, 7 into 10 power minus 10. And this is some 0.523 into something. Then the second component is, so basically the second component of this is converging to 0. So the second one is actually 0. First one is 0.5. The last one is 0.523 something. So this, since it is converging to 0, you cannot compare the values. So this is something into 10 power minus 10, 10 power minus 18 are too small to be compared. But it has already converged. Basically, this has converged in 3 iterations. So for the problem in the assignment, it is advised to use coding or Excel. That is 2 degrees of freedom, so you can do Excel, but it is prone to mistakes, so better do coding because finding inverse is just one step. So define 2 functions, one to find the residual, one for finding the tangent. These 2 functions are very easy. Just plug in the values and return the vectors. Here the logic is start with an initial guess, then inside the loop, do the 2 steps. One, form the residual, form the tangent, invert and find out the increment, update. So these 4 steps are the core for programming. Set any tolerance and you have some tolerance this thing criteria. So this one converges in 1, 2, 3, 4, 5, 6 iterations, even if we set 10 power minus 6. So maybe that's the end of this session and also the end of the problem solving for this course. So I hope this was useful. You had something to learn from. I enjoyed doing some of these. I learned a lot of things while doing this. So as usual, I'll upload the video, and in case you have any doubts, you can write to me always. So this is my email, nareshc@iisc.ac.in. You can write to me in case you have any doubts. I'll respond within a day or two. Yeah. Yeah. Any other doubts you can?
Naresh,
Yeah.
when I saw the Google Drive folder,
Yeah.
there was no any PDF for most of the weeks there.
Oh yeah. I didn't upload because mostly it was like it is scribbled like this. I couldn't put that in place. But if it is useful, I can put. I'll put
Actually,
it. I have it.
yeah,
Yeah.
yeah. Please upload these PDFs on the Google Drive folder. And
Okay.
one more thing, this was the last problem solving session, as you told.
Yeah. This will be the last.
Okay. Mm, so, can you conduct one session which which we can get for the entire course doubts? Means that will be the cumulative actually.
Okay. Yeah. So I could have conducted. Uh, the thing is, they sent a form last. Uh, early in September, end of September, they sent a form asking if I want to conduct another session or something. At the time, I missed filling the form. Uh,
Yeah.
but I can tell them that some of the students are requesting, and at that time I forgot. But if it is possible, I'll take next Monday also.
Mm-hmm.
It's not hard for me. I can do. It's just like revision of everything else with some overall doubts, right?
Mm-hmm.
We
Yeah,
can
yeah.
do that.
And one more thing regarding this, non-linear FEA.
Yeah.
In general, when there is no any convergence for the
Okay.
non-linear problem
Okay.
due to some extra large non-linearity, or we can say means whatever it be.
Mhm.
So basically, in general, what we can see, there is one other concept, that is bisection is used.
Okay. Okay.
Bisection is used by any simulation software, any
Okay.
commercial software. Okay,
Okay.
and what software does in that bisection basically,
Mm.
it generally increases the convergence criteria, and
Okay.
using any of the non-linear iterative method like Newton-Raphson or line search method or whatever it is, it will then do some iterations, and
Mm.
now on the basis of new convergence criteria,
Mm.
it will calculate whether the convergence we are getting or not. So
Okay.
in terms of this theoretical perspective, I want to know what is the meaning of bisection basically.
Bisection, I'm not really sure. Bisection, I only know the root solving method, which is the bisection. But what here they mean by bisection? Uh,
Actually, in general, when I put this term on Google,
okay.
what it tries to say that when there is much more difficulties for any non-linear solving simulation software to
Okay.
get the convergence criteria,
Uh,
then it will always try to increase the convergence criteria on the basis of the tolerance value, just like this it says. But I am
okay.
not getting the actual meaning what Google tries to say on this favor.
Oh, okay. Okay. Maybe I'll
Yeah,
also
that's
look it up, and then I'll get back. So what I can understand is finding this tangent is very hard sometimes. So
okay.
for some really elastic
Mm-hmm.
plastic is still fine. For some, when you have large plasticity and damage and stuff, finding the
Mm-hmm.
tangent is not easy. For finding the tangent itself, it may require a lot of iterations. In
Mm-hmm.
those cases, so a Newton-Raphson requires a tangent. That's an issue, right? So Newton-Raphson without tangent, it's not going to work. So when we can't find a tangent, maybe it resorts to something like bisection algorithm for solving the nonlinear equation. So if we can bound the root between two values, you can do bisection. But I'm not sure how they do it for vectors. Bisection in scalars we know, but uh, yeah, Newton-Raphson, the only disadvantage is for very hard problems, finding the tangent is difficult. Otherwise,
Mm-hmm.
Newton-Raphson is fine. And
Mm-hmm.
when the tangent is singular, that is another issue. So in that case, we have to go to arc length or something.
Okay.
And bisection does not require a tangent. You can always bound the root and keep on uh, approaching the root in a manner, but that will converge slowly. It will require a lot of iterations, but every iteration is very fast. Compared to
Mm-hmm.
Newton-Raphson, one iteration is very fast in bisection because it requires only and stuff.
Mm-hmm.
So, but that
Okay.
is the root solving. Yeah.
If you use any structural simulation commercial software
Mm.
at your end, if you have license, for
Okay.
example, you can use Abacus CAE or NSys Workbench,
Sorry.
NSys Mechanical, those. Are you getting my point?
Sorry, there
Hel-
was some issue.
Are you getting? Hello? Hello?
Hello. Yes, yes, I
Hello?
can hear you. So if you said if we use any commercial software for simulation,
Hmm.
what?
Uh,
I didn't get the
and
question fully. What was it? If
okay,
we use any
okay.
commercial software for simulations?
Actually, I want to try to elaborate where I have seen in my entire career
Ah,
this type of bisections actually. For
okay,
example, in a very complex assembly where you have welds also, where you have
okay.
bolts also, where you have some torsion springs also, 1D
Mm,
elements also. Okay, in those particular, for example, in a particular area, there are some linear contact and there are some non-linear contacts also, and those non-linear contacts are still in a very small area. So there,
okay,
the order of non-linearity will be very large in for that particular situation. Okay, and to do
okay, okay.
some approximations,
Mm,
always I have seen that Abacus CAE has tried to do some iterations to get the value of the variables on the basis
Okay.
of the convergence criteria. So when
Okay.
there is highly non-linear context in a very smaller areas, this
Okay.
type of bisection I have seen used by these commercial softwares. So you can think in this perspective also, and you can search at your end whatever you
Yeah.
can get. Okay.
Yeah. Yeah.
Actually,
I'll.
there are a lot of more things I can ask, but you know, this doubt session is not so sufficient for that, because that
Yeah.
is the more practical way of thinking, basically. Okay.
Yeah. Yeah.
And I always try to relate my academic concepts to what I am doing in my industry practices.
Hmm.
Okay.
Okay.
Okay. Yeah, yeah. Okay.
I'll see.
Oh.
I'm not sure about next session. I'll write to them. But
Mhm.
yeah, you have email address or something, so that how do I contact you in case there is another session, or because it may not be on
Yeah, yeah,
Mondays.
yeah, 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 yeah. I can give you. You can
Yeah.
just write. You can just write.
Minute. Yeah.
Uh, AMAN Aman
Eh, Aman.
SONI
Okay.
98
Okay.
1994.
1994. Okay.
Yeah, @Gmail.
Okay. Yeah, in
Okay,
case
so
there's another session, I'll write to you. In case they don't agree for another session, uh, I will still write to you. Maybe you can discuss on another Teams meeting, not in that this link.
okay, okay,
Yeah.
okay, 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 okay. Just
Yeah.
thanks for the
Yeah.
support.
Yeah. That's okay.
Okay,
Yeah. Okay.
okay,
I'm
Naresh. Then.
recording here. And anyway, thanks for joining all the sessions. We'll